Yeah, so here we're saying these guys are simply a complicated version or a sophisticated version of glycerides, except one group is replaced with the phosphate group. Now I have something that I needed to show us here. This head, the head is the phosphate group. So on the bended part, yeah, you did well asking the question. On the bended part, that's why you replace the phosphate group, because we need to create a head, and it's best created at the bended section, because phospholipids are known for maintaining the integrity of the cell in terms of not just supporting them in the structural form, but also the main purpose, which is creating this phospholipid bilayer, where there is like this this illustration here tells us the extracellular space, the outer part, and then the inside part of the cytoplasm. So it makes the cell membrane to be selectively permeable. When you say selective permeable, it's because of the middle part of the membrane is made up of phospholipids, which are having a head which is hydrophilic and a tail which is hydrophobic. Yeah, so this helps us to maintain the rigidity of the cell in terms of the water content of the cell, because the middle part hates water. Some small quantities of water may be squeezed within, because this part of course likes water, but for them to actually pass through here, only a small portion will be able to come out on the other side. Yeah, because most of them will be pushed out through the sides. Yeah, so this helps maintain a good atmospheric environment in terms of the water levels. Yeah, so on the phosphate group, just always know they like this under multiple choice question. The phosphate group has no double bond. It's only phosphorus bonding to 4 oxygen atoms, and this is what you have. Yeah, so
it has no double bond.
It has no double bond. It has single bonds throughout. It's simply saturated. Yeah, it's a typical illustration of a saturated fatty acid. Yeah, so it's like now we're just trying to dive in to talk about the types of fatty acids. So this is what we are having. Yeah, is there a double bond here on the phosphate? Only in this. Oh yes, there is a single. Yeah, so there is a single double bond. Let me add that. Yeah, so the other structure, they had added water already. So here, if you notice here, there's a double bond here between phosphorus and oxygen, because oxygen has a covalent number, has a valence of 2, meaning it needs 2 electrons for it to be happy. So the other reason why this guy is polar is because it has a positive tail and also a negative head. Yeah, so the electron cloud, because of having oxygen, these 4 oxygens, makes it to be positively charged or partially. So the dipole moments here will make this to be polar. That's what we have. Any questions here? Is this okay?
Yes, that is okay.
Yeah, then this is when it's just, in case you're wondering this thing here, this is when it's in a straight line. You are seeing this guy that we are saying in a straight line. It looks nice like this. When we put it like in a rectangular form, it can look like this. But then whenever you expose water here to the middle part, what happens is that this thing is going to curl up, because this part does not like water. So it's going to shrink, only exposing the 2 sides that like water. That's the reason why you are seeing it looking like this. So the middle part, this is supposed to be closed. Initially, it's supposed to be closed everywhere. So it's supposed to be closed even here. They're just showing you what happens to the inside part. Yeah, so it moves away from water, only exposing this part, which likes water. Now you're seeing it. So it can be in this form sometimes. It's not always going to be linear. Yeah, and another form that lipids can take are simply waxes. So waxes are mainly esters of fatty acids with long alcohol chains. So they are used in waterproofing material by plants and animals. That's the simple logical reason why water cannot enter a plant through the leaves, because the leaves contain waxes. Yeah, so that's what you have. In plants, they form an additional protective layer on the cuticle of the epidermis of the leaves, fruits, and seeds. This maintains what the waterproofing can work in both ways, in terms of trying to reduce what do you call that? Is it transpiration or the loss of water by the plants whenever there is less rainfall, less water supply? So the presence of waxes in the leaves is important for that particular purpose, and also in the seeds, because some seeds can be stored in harsh conditions, but if you just put them in good environmental conditions in the soil, they'll be able to spring up, to produce, right? So this is how the seeds are protected inside, because of being surrounded by a good layer of waxes. Yeah, so in as much as it's a seed, but it has like nutrients, it's stored nutrients within itself to maintain itself until a good certain period of time. Under they always put expiry dates on all the bags of seeds that we purchase. Yeah, so they give us an illustration here how the ester bond is formed. So this is going to be called esterification. Produces what we call ester bonds, or some people say ester linkages. Yeah, so we can say ester bonds. When esterification occurs, we call the bond created as an ester linkage or an ester bond. So this is a typical illustration of how waxes are formed. It's very long. They're giving us, this is called a skeletal structure of a molecule. It's irrelevant for you to know it here in bio, because you won't be writing these structures in skeletal form. What I mean by skeletal form is it shows the bends wherever there is carbon. So like this guy here, if I give you this, then I put a carboxylic this side. So each carbon is going to be represented by a zigzag. So each carbon, so one carbon, a tip and a turn represents a carbon. So one carbon, that's here. Then this guy is there. Then I'll say this. The how many? 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. Then I show my double bond there. Then I show my oxygen there. So in a skeletal structure, carbon atoms are not shown, and also hydrogen atoms that are attaching to carbons are also equally not shown. But you know, in the back of your mind, you know to say there are hydrogens everywhere here, because each carbon needs to have 4 covalent bonds. So this is where this is coming from. We only show oxygen atoms and hydrogen atoms when they are bonding to oxygen, like this in this hydroxyl. So one hydroxyl here and one hydrogen there, producing the water. Then the ester bond is created. This is the ester bond that is created, and these are very big. No wonder they rarely melt. It's like that thing. I don't know whether you've seen the thing that women used for them to polish verandas, and although some of them melt the candles, right?
Candle wax.
Candle wax, exactly. Yeah, but there's that actual wax. It's a bit that stuff that they put. It's the same. It's a good application of this. Yeah, so it's a special type of wax. Sometimes this is beeswax. You can have this domestic example of a wax is simply beeswax, which is a special type, honeycombs. The bees use it to store honey, to protect the liver and the pupae. These are simply the stages that the bees take for them to mature, right? Yeah, so
Yes.
You've seen those white things in those honeycombs, like those guys who harvest honey. They're those white things that are always next to the honey, right?
Yes.
Yeah, that's what we are calling the bee wax. It is used in glazing agent of fruits, coating agent in cheese, chewing gum, in lip
Is
balm.
it edible? Like on its own?
It can be edible, but then it's tasteless. Yeah, so we just add it to things like, let's say, lip balm or lipstick or even chewing gum. So yeah, if you're chewing gum, it's okay. There's a point where you can actually chew the whole gum for it to disappear. No, it doesn't disappear because it's not soluble. It's very, very not much soluble. So it will still be there, but it will be tasteless at the end. Yeah, so the only thing they do in the production of bubble gums or chewing gum, they'll just add some sweeteners to it. Yeah, added a few carbohydrates, just make it sweet a bit, and some color, but then at the end it will just be wax. Yeah.
Yes.
Yeah, so you have that. Shoe polish, these are just typical illustrations of where we can find applications of where wax is used, this type of wax. Then the last type of lipid that is always abused as steroids. So these are special lipids compounds with 4 rings, which are found in plants, animals, and fungi. So this has a network of, these are benzene ring, because these are, sometimes you can call them cyclohexane rings, because these are, cyclo means it has it's in a circle form, it's in a ring form. Yeah, so anything that's in a ring form under organic chemistry, we call it cyclo. So we put a cyclo in front. For example, if I give you this, I give you this guy here. So initially this is hexane because it has 6 carbons. Now if I remove 2 hydrogens and connect these 6 carbons, I'm going to create something that looks like this. Now to avoid rewriting the carbons, we're going to write this in a skeletal structure where the carbons must not be shown. So this is going to be something that looks like this. So these are the 6 carbons that we're having. Now we are having 4 of them in this case. Yeah, so we have this guy, we have that, we have that, we have that, and a hydroxyl group protruding this side. So this is the structure of steroid, and then this here is the structure of cholesterol. So don't be shocked with these guys that they're showing here. These we call them wedges. These wedges here. So they are broken wedges, then they are solid wedges. The broken wedges show us molecules that are protruding out of the paper. This is viewed in 3 dimensions. Yeah, so this is it's like Munga Ichem 3D. So if I give you something like this to say carbon, then this is like that, but hydrogen, and one is solid like this. So the solid one simply means that this is how do we say, this is away from you, then this is towards you. Yeah, this is towards you. Then those single ones, those smaller ones, are the ones that are on the plane. These are on the paper. Yeah, so this is just how we write structures in 3 dimensions to show to it to say one thing is there, one thing is outside. So this is like going away from you. So it's like inside the paper on the other side. Then whenever it's broken, meaning it's towards you. Then whenever it's just like a solid single line like this, means it's onto the paper. So this is a bit irrelevant for you who is doing bio. It will be relevant when we do organic chemistry, yeah, in chem. So for now, you just have to sort out the structure to say this is how steroids look, and this is how cholesterol looks. So this is basically the structure that you have. So there are a bit of some connotations, the side effects rather, to the excess taking of these same steroids. The large number of CH groups make steroids non-polar. So these guys are non-polar, meaning they rarely dissolve, right? So abusing them, because they're found in things like those fitness gym protein shakes and other things. They are good for muscle building because they can be a good source of energy, but excess taking of them can actually, in terms of, it can increase a normal illustration I can give. It can give an increase in the number of times someone can actually have muscle pulls. Yeah, so if you take them excessively without taking other supplements to break them down, because when we say something is non-polar, specifically we mean it being polar in water. It doesn't mean it entirely doesn't dissolve. Yeah, so it does dissolve, but not in water. So you need to take something to dissolve it. So because of the network, a larger number of carbon to hydrogen groups that are present, then the most type of animal steroid is cholesterol, which is important part of the animal cell membrane and structure. So this is a very important part. Cholesterol is also a precursor to fat-soluble vitamins and steroid hormones, sex hormones. So you've heard people use steroids before, right? I mean the word
Yeah.
steroids, right?
Yes, like for during the Olympics when they're disqualifying people who have used
Exactly.
steroids.
There are people, so it can also increase the hyperactivity of someone. Yeah. But then it has to be gotten out of the system as quickly as possible. Yeah, because of its side effects. Yeah. So this according to this file, this marks the end of lipids. So what I'll do is try to find the Shihata notes to see if I've skipped anything. Then I'll try to notify you, but I doubt. I think the only thing you have to pay attention to are the structures in the Shihata notes because they're more elaborate. Like here, this is just a skeletal structure. They have not shown the hydrogen atoms this side. Yeah, there's a part where you have to identify the type of covalent bonds that are present, how many pi bonds and how many sigma bonds. I'm not sure if you've done that part already in chem, but I've taught people before who've covered that before. But even here, sometimes you find in Shiata notes, it's nicely illustrated. They'll show you how many pi bonds are present, making it obvious for you because you know now as a chemistry student, you know when pi bonds are created, you know when sigma bonds are created. You know to say this is when you have an s orbital and a p orbital, so all those things. It explains why this guy is partially soluble in water, or rather completely non-polar to some extent if there are a lot of them. Yeah, so
Yes.
yeah, this mark